But I think it's important given the comment that I did at the beginning of my presentation. I didn't comment very much on the radius of the photosphere, so this is a typical place where we think that the kilonova light is generated. I just then want to go back and just have a look at this number. It's 10 to the 15 centimeters. So we are a fraction of a light year away from the central object. This is once again to remark you that we are dealing with two very different scales. The merger happens on a scale maybe of 10 to the 6, 10 to the 7 centimeters. This is the length scale of the remnant. This matter, before becoming visible to us in the kilonova, must expand by several orders of magnitude. So the kilonova emission happens far away, and the time that it takes for the ejecta to expand, that's why it happens at 5 days after the merger, because we have to leave enough time to the ejecta. Okay, so let's go a bit on the modeling, but with an eye on what we have observed. So you know that on the 17th of August of 2017, there was the first gravitational wave detection of an spiral of a binary neutron star merger, and then this was followed by first the detection of a gamma ray burst in the compatible area of the sky. And this has, of course, furnished a furious search for an electromagnetic counterpart that was successful. So 11 hours after, we have started seeing light from the kilonova associated with this event. And in particular, roughly speaking, we can actually say that there was two different components in what we have observed. If you just look at, there was a bright ultraviolet component that has a peak around 1 day, even if actually the largest luminosity, so the smallest magnitude, was actually in the first detection, so we have still an uncertain what could have been before that. And followed by what this picture has been shown yesterday by Neil Tamir also, so this is actually the infrared component. This is what we would have expected, and just look at the 5 days peak, for example, in the K-band in the infrared. And moreover, we have the photometers, of course, we have also the spectral information, things like, so an instrument like X-Shooter was able actually to provide a very nice spectrum from a few days, 1 day, up to 10 days, different wavelengths. This detection, of course, has somehow triggered a burst of enthusiasm, of course, but also of activity in the people that try to understand what did we observe. And when the paper of the detection came out, there was also the paper of the astronomers or the astrophysicists that tried to give an interpretation of what we had observed. And people using a model very similar to what I showed you before, tried somehow to fit the curve that they had at that time. And one of the things that emerged was that if you try to just take the spherically symmetric model that I showed you today, and you try to search for a combination of mass, opacity, and velocity that could reproduce what we have observed, actually you don't do a very good job. For example, here people were fixing the nickel mass, and as you can see, maybe if you can get some points here, you still miss the peak here, and of course you have completely wrong infrared behavior here. Then people said, okay, but this is not nickel decaying, it's our process decay, so we just put the parameter of the blue kilonova with the same opacity, so assuming that neutrino, for example, were able to prevent the formation of lanthanides, and again, the job is actually even worse than the nickel, so we completely ignore with the blue kilonova model, where blue stands for the fact here that kappa is small, we miss the infrared. Then people started to say, okay, try to get a better behavior at a later time, but then let's put a larger opacity, but then not only we miss the infrared component, but we also miss here completely the visual component. So people were starting to be a bit puzzled by the fact that even try to optimize your code in order to find the best kappa that can fit, you still are doing a pretty poor job. So it was clear from the modeling side that the simplest things that you can think about, something that is spherically symmetric, that is characterized by those three numbers, could not catch what's going on there. Then people started to say, okay, why do I have to stick on one kind of ejecta? We have said that there are dynamical ejecta, that there is the winds, that there is viscous ejecta, each of those has different properties. Then I can just take several of my models and just, if you want, sum them together. So assume that there are different sources of Kilonovae emission, and they just are at the same time present. And as you can see here, somehow you can do a much better job. This is a simulation result of a work from Villar and collaborators. So you can actually end up with a pretty nice agreement. But from a conceptual point of view, you have in this kind of work, people, as I said, just take 2 or 3 spherically symmetric models and they just sum them together. What does it mean? It means that by construction, you are taking a triple, so a set of 3 parameters, the ejecta mass, the velocity, and the kappa, and you are building a correlation among them. You assume that you have a certain amount of matter that expands with a certain velocity, with a certain opacity, still in a spherically symmetric configuration. This is, for example, from the paper. This is there is another point that from, say, if you want to be a bit critical, you can say, well, you get a better agreement because you increase the number of parameters. This is the price that you have to pay. In some sense, we are giving more freedom to the system, and it's easier to find a configuration that can adjust to what we observe. But maybe this is what nature does. Nature is not necessary to be always simple and fair with us. It can be complicated. And here you can have an example taken from the same paper as before. These are the best fit value. And you can see how much parameters could actually enter in your calculation. And this is the result. In the Tambi paper, there was also example of the light curves. That this is another approach. So instead of fitting your parameters, you can actually construct some light curves based on detailed models. And what you can do actually is to try to see which is the curve that fits better the data.
Sorry.
Yeah.
I have a question. So when you speak about multi-component, you're saying that you're adding all the sources of ejecta, or you're just adding another triplet of mass, velocity. So are you thinking about the fact that there are many sources, or this is just a way to say, okay, that's why we add another component? I don't know if my question
this depends very much on the details. There is not a unique answer to this question, in the sense that, for example, in this work here, what people say the 2-component model is really a triplet. So they have 2 triplet of parameters, each of them has a spherically symmetric model, each of the model gave a luminosity, and what they do is just they sum up the 2 luminosities.
Yes, but you are saying that these 2 components, one is for one type of
exactly.
ejecta, the other one is for
exactly.
the other.
So you can
so
tag.
you are thinking about the.
Exactly. So you tag each component with a set of M, V, and kappa, and you run your spherically symmetric model. However, there could be a conceptual problem in that. And if you remember, we have seen that, for example, the dynamical ejecta could have a different property according to the fact that you are looking from the pole or from the equator. So nature can be a bit more subtle than that, in the sense that not only we probably need to take into account different components, but we have maybe necessarily also to break our idea that nature must be always spherically symmetric. So we can actually end up with models that not only have different components, but inside each component they have an explicit dependence on the angle, such that if you look at the system from polar angle, for example, you will see matter that has a lower opacity because it did not produce lanthanides, but if you look at it from the equator where it produced lanthanides, the opacity is larger because kappa increases. Okay, so in some sense, after the initial analysis, people is now recognizing at each level that we need to take into account also this complex geometry. So the most recent geometry that you can think about, for example, this is a recent paper from Bulla and collaborators, they also assume, for example, in a radiative transfer code, that the polar ejecta is actually lanthanide free, while the equatorial one is lanthanide rich. What is actually the important thing of this thing? That since you break the symmetry, it's important where you are looking at. If you're looking at the system from this point here or this point here, you can have potentially different Kilonovae. And in fact, there is actually an explicit dependence on the observer viewing angle. This is something that also we have explored. So with just a model that just implements, if you want, this scheme with the equation that I've shown you before, but breaking the spherical symmetry and do things ray by ray, we were able, for example, to fit also decently the data. And so this is not, I mean, there is a lot of works. I try to cite most of them. This is what we have done. And we also confirmed that with a 2 or 3 component model, you can actually fit the data. But since now we have an explicit dependent on the angle, for example, we were also able to constrain in an independent way the angle at which we have observed. And it came out that this angle should be of the order of 30 degrees. So it's like the kilonova that we have observed, we should have probably observed it closer to the pole, if you want. So from the above rather than from the equator. And this just came out from this kind of analysis. It's very simple analysis, but this was one of the results. These kind of models, they are also, roughly speaking, a sort of agreement. It depends on how many digits you want, but if you just collect from the literature the different results, you will find that within a factor of 3 or 4, the amount of ejecta was more or less consistent among different works. We are speaking about something of the order of a few percent of the solar mass, with more detailed models tending to having this number a bit smaller, but still it's compatible with all the kind of ejecta. There are so many kinds of ejecta and ejection mechanism that the number that we found is still compatible with what we have expected. But what was really important, at least from my side, was that if you want to explain the blue components here, especially this behavior here, you do need to take into account the fact that neutrinos were active inside the system and they act lower a fraction, at least a fraction of the opacity through the action on the Earth process nucleus. This is something that we have done later. Okay. Now the question that we want to answer is, can we say that, for example, Kilonovae is a standard candle? Do we expect an intrinsic variability, or if we, in the future, we will be again able to see a Kilonova, we should expect something very different? This is something that at the moment it's very difficult to answer because there are a lot of uncertainty, but my opinion is that given the intrinsic variability that we expect, because we can have different amount of ejecta, we can different outcome of the merger, we can form a black hole or not, I would say that it would be very surprising for me if Kilonovae are standard candles. I do expect an intrinsic variability. This is shown in this figure here. For example, the 3 different plots show the Kilonova light curve computed with the model that I showed you before in 3 different bands. So the G band is in the visible, and the Z is just between the visible and infrared, and then this is the KS is the infrared band. The difference between these 3 different models is that we have computed the Kilonova light curve for a case where when the collapse happened, when the merger happened, the result was the formation of a black hole, the prompt formation of the black hole. And you can see that the Kilonova, compared with the other 2 cases where we have short-lived hypermassive neutron star. So here we have an hypermassive neutron star phases that after roughly 10 milliseconds collapse to a black hole. And here we have a long-lived massive neutron star. The equation of state is sufficiently stiff that prevents the collapse of the system. So they are very qualitative different outcomes of the merger, and the good point is that this has also a qualitative different outcome in the Kilonova. In particular, if you promptly form a black hole, the Kilonova tends to be fainter and tend to concentrate during the first day. While if you have something that is a long-lived massive neutron star, you tend to have a Kilonova that is brighter in all bands, but it's also more extended in time. What is the physical argument behind that? As I told you, you have to consider how much mass is ejected, and if you form a black hole, you don't have time even to eject a large amount of dynamical ejecta, because when the 2 stars just crashes, if you immediately form a black hole, for example, you cannot do the shock-heated ejecta, because this comes from the dynamical interaction of the 2 cores. If there is no more cores, if there is a singularity, there is no way for the system to eject matter. Moreover, if you form quickly a black hole, you will not form a disk. But as I told you, it could be that most of the ejecta comes from the disk. If we don't form a disk, we are actually removing the largest source of ejecta. So it's not surprising that a prompt black hole formation will end up with something that has a much fainter kilonova that only is during the first day. While if we have something that is long-lived, we will have something that is much brighter, that extends much more in time, because we simply have more masses that can decay and then become transparent much later. Actually, we have collected a lot of simulation, and so 35 binary-star configuration. For all of them, we perform numerical relativity simulation, such that we have the dynamical ejecta, we have the disk, and as you can see, there is here what we have is the peak time. So again, the 3 different bands. We have the peak time, the peak magnitude, so it is the magnitude at the peak, and also the peak width. So how long does it take for the peak, for example, to become fainter by 1 magnitude? And as you can see, there is always a trend with this lambda tilde. It's the same quantity that I showed you today. This is once again the same idea, to just see in a more systematic way. If the lambda tilde is large, you form a black hole. And for example, if you form a black hole, the kilonova is faint. If lambda tilde is small. If lambda tilde is large, then you have an hypermassive neutron star, or even a stable massive neutron star, and then you have a lot of time to emit matter, to irradiate with neutrinos, and all these processes tend to produce something that is brighter. Just from this graph here, you can get a feeling also what is the expected range, for example, of a magnitude peak. So this is of course for a fixed distance, this is absolute magnitude. So we could have actually an intrinsic variation of the order of 3 magnitude just from this calculation. Now what I would like to say in the next few slides is, I've shown you a model that gives you the possibility to catch the physics that is happening behind the kilonova, but it's still a rather crude model. In particular, for example, if I have to estimate where is the luminosity peak, or what is the luminosity, I just use some timescale argument. Of course, this is not state-of-the-art. State-of-the-art model of the kilonova are actually provided by so-called radiative transfer. The radiative transfer, it's a very complicated problem. So the idea is that you really try to solve the Boltzmann equation to model the propagation of the photons through matter. This is, of course, something that you have to deal with a lot of assumption, a lot of approximation in some sense, but it's actually the closest solution that we have at the moment to the proper Boltzmann transport problem of photons. Usually people use these Monte Carlo schemes where the idea is that you just model your photons as a package of energy that can just have a certain probability to interact with your matter. So you have to imagine you set up a background of matter, then you initialize some package of photons and you just see how they evolve. It's computationally very expensive, but it's the only way that we have at the moment to properly tackle the problem of what is the outcome of a kilonova. The R process element's opacity is one of the key ingredients. Let's say these kind of models have been developed for many years in the context of core collapse supernovae and tape 1A supernovae. So in principle, one could think about, okay, I can take the same technology that have been developed and that helps us a lot to understand, for example, the kind of ejecta from this kind of stellar explosion, and I can take it directly to the kilonova business. However, there is an important difference. It's the opacity. In this graph here, you can see, first of all, that the opacity that up to now I told you that is one number is not one number, it's actually a function. So the number that I gave you before, you have to think about as a sort of mean value of the opacity. But if you do proper transport calculation, you have to think about that the kappa that I showed you depends on the wavelength. And look what is happening. Oh, there is no y-axis. But it's a log scale. Sorry, because I took the panel B, probably it was on panel A. Sorry, but still, this is 1, 2, 3, 4, 5. It's 6, 7 order of magnitude for a wavelength that goes from the ultraviolet to the infrared. And you can see also how dramatic, so there are several take-home messages from this picture that should be taken. First of all is that there is a dramatic dependence on the wavelength, so it's really important. The second thing is that it's a forest, it's not a smooth line. And the reason is that, you remember, what is the origin behind the fact that we have high opacity if you have lambda 9 rich, is that we start populating the F shell. If you start populating the F shell, the major source of opacity become bound-bound interaction. Bound-bound interaction in an F shell means million of possible different lines. So each of these is potentially one of these lines. And this is what also Neil was saying yesterday, that it will be very challenging to detect one single line because we have a forest of them. And they have, moreover, they are broadened by several Doppler effects. So it's really, really challenging. People as to even doing proper transport, you have still to deal with approximation. So how, for example, to translate this in a discrete number of energy beams, people using approximation like the Sobolev approximation. This kind of models started in 1D because they were imported from core collapse or from tape 1A, where things are initially more spherically symmetric, but since we have learned that binary neutron star merger or compact merger in general are highly aspherical phenomena, people have understood that they have to go to multi-dimension. Of course, doing a Monte Carlo radiative transfer in multi-dimension is extremely challenging. At the moment, there are a few groups all over the world that can do that, not so many. And here I'm just reporting some of the results. This was published actually at the time of the detection, and people applying this kind of models, they were able, for example, to extract spectra and to compare these spectra with what we have observed. For example, this is from a group, Tanaka and collaborators in Japan, then there was Darkese in the US, and there was also a group that was working in the Los Alamos laboratory. They were all able to extract spectra. Nowadays, yesterday was mentioned by Neil the existence of this Engrave collaboration. Now also Engrave is developing this kind of expertise. So for example, the work of Mattia Buda here is one of the possible, and the other group that is working on that is using the TARDIS code. So the hope will be that with the next Kilonova we will be hopefully able to provide the detailed spectra. But if you want to provide detailed spectra, so getting really the physics of the atmosphere right, so that you know what is the behavior of the photons that are emitted at the photospheres and they can still interact, such that you can explain all these small scale features, you do really need this kind of radiative transfer that are state of the art but still in developing and still very expensive models. This is what I wanted to say about state of the art modeling. This concludes a bit the Kilonova part. Is there any further question about that before going to the other electromagnetic counterparts? Yeah.
A little question. You mentioned that we model multiple components that have multiple different properties, but we just sum them up. Will it be useful not to just sum them up, but somehow account for possible irradiation of one component by another component? And is it possible to do it simply analytically, or we need a radiative transfer for that?
So, as I said before, it depends very much on the details. You have to really look every paper what the people are doing. In some of the paper, people look at the luminosity and they just sum them up. This is one approach. In some sense, you are forgetting all what you were saying. You are just assuming that there are two sources that maybe happens in two different regions of space. They just propagate without interacting. In the model that we produce and you are using, starting using, there we do take into account a bit this, in the sense that the luminosity from, it's like you have different photospheres, and the luminosity from the lower photosphere does not contribute to the spectrum. It's like we are assuming that these photons get reprocessed by the other and get reprocessed by the others. This is somehow a patch. It's not really what you expect because you have still to make some assumption. Radiative transfer in multi-dimension is the only way to take this properly into account. But this means also that, for example, you cannot use some of the approximations that are used in some of this radiative transfer that always anyway assume a light bulb at the photosphere. So you really need to take into account multidimensional, multi-component, time-dependent radiative transfer. There are very few that can do that, and it's very expensive. This is what should be done. My personal opinion is that we need to do this kind of simulation in order to get the right answer. But then if we want to employ this physics in a meaningful way and to run your, I don't know, Bayesian analysis on that, we need to find a simplified expression because these three-dimensional, time-dependent, multi-component, anisotropic things, they are extremely expensive. So I think it's totally a fair question, it's a good question. we have to pay attention to this interaction. And it was recently shown in a paper, I don't know if I cite it somewhere, but by the Tanaka group, that they found something similar to what we found also with our more naive approach, if you want. So the interaction between the geometry and the different components, it's important because photons from an inner photosphere can be reprocessed to a completely different temperature. So I would say it's an open, if you want the short answer, it's still open question, but relevant. Yeah.
Another question. In the case of black hole neutron star mergers, like in the case in which the neutron star is directly swallowed by the black hole,
Yeah.
are Kilonovae expected in this case? Like
Naively, I would say no.
no.
I think you need to invoke some more exotic physics, because if it's totally swallowed, then there is nothing to be expelled.
Maybe some mass shedding, it's not enough. Just the mass shedding before, so there is no tidal disruption, but maybe there can be mass shedding, but it's not enough. So we do not expect any electromagnetic counterparts from.
Let's say if we trust the level of the simulation that we have at the moment, we don't see any of those. Of course, it's questionable how good we simulate neutron star, for example, the crust during this. It could be speculative, but maybe there is some precursor. Maybe when the neutron star has, we assume that it's a perfect fluid, but it has a crust with some plastic properties. It could be that before getting swallowed, it just get deformed, and then there could be some X-ray emission similar to this star quake that maybe powered the X-ray class of X-ray burst that we observe from magnetar, for example. This is one of the possible interpretations. I don't remember the name now. They have a name. But yeah, anyway, field configuration with break in the crust can also power flashes of X-ray, and this could be a precursor. The problem is that you don't know exactly where to point your telescope before the merger, because you don't have the trigger. But maybe in the future.
Say nothing that we discussed today is expected.
So once again, short answer is no.
Yes.
But I would leave it open maybe to some more exotic physics.
Thank you.
Okay, so this concludes a bit what I wanted to say about the Kilonovae. It was a long trip. Now let's move. Yeah, there was a question.
Yeah, I have a question related to research.
Yeah.
You said about neutron star and black hole, right? The neutron star has lower mass than the black hole. Is neutron star has higher mass than black hole? I know it's unlikely to
Well.
but would it be different?
Oh yes, but it's different also if the black hole is more massive, but not enough to swallow completely the star. So, for example, if you have a 5 solar mass black hole and a 1.4 neutron star, very likely you will actually form a disk. Well, not very likely, because in 50% of the cases the spin is counter-aligned and then you swallow it anyway. So, but let's say in a quarter, let's say roughly speaking, in 25% of the cases, if you assume a flat distribution of spin, you already expect the disk. And if you form the disk, you will have your kilonova, maybe your gamma ray burst. So yeah, so your comment is totally appropriate. If the mass ratio is not extreme, we do expect the formation of a disk with a kilonova and with the gamma ray burst.
Yeah, my question was actually, is the neutron star has higher mass than the black hole?
Well, then I think it's even. Say, I don't want to say something wrong, but I would say that it's plausible. You will form a very massive disk. So you will have an even brighter kilonova. The only point is that from an astrophysical point of view, it's very hard to get a black hole. Maybe you need some primordial black hole, because I think from stellar physics, it's very hard to get a black hole that it's below the maximum mass of a neutron star. I don't know if there are, Sebastian, maybe you know, is there any numerical relativity simulation that has an inverted ratio? So we don't know exactly what will come out. Naively, I would expect that the black hole at a certain point depends on the mass ratio. That's a good question. Maybe we have to still to answer it. Probably it was not People didn't think that it was a physically relevant case because we don't expect black hole of below 2 solar masses, and then it has not been investigated.
You said that you don't expect that Kilonovae will not be standard chambers, but it's very different. But in case of Novae, there are some old models, old correlations like Marty relations or RPR relations for determining the distance and the composition. It's measured from the maximum magnitude and the Ziming times, T1 and T2 times. Is it possible to make such model for Kilonovae to determine the distance or the mass model?
Let's say these plots seem to suggest that maybe it's possible, in the sense that it's not a scatter plot. We found, for example, this lambda tilde, that things seems to have a weak correlation with that. So I'm not saying that things are not under control or stochastic. I'm just saying that it's not that we expect. So I didn't know, maybe standard candle was not a good way to phrase it. I don't expect all the Kilonovae to be identical. Then there is a correlation such that if maybe we will measure lambda tilde, we could already foresee which are the measured properties of the system. This is what this plot seems to suggest. So it could be that if we are lucky enough, they are not identical. There is not one standard Kilonovae and they do all the same, but there is maybe still a clear correlation with some intrinsic parameter like lambda tilde. Actually, I think I have maybe a partial answer to your question. There was 2 years ago a paper from John Fuller and collaborators, and they actually investigate the possibility that the primordial black hole collides with a neutron star. Primordial black hole could have a mass of a few solar masses, a few Earth mass, so something very small. This is very hard to simulate, but there have been some simulation performed by David Radice. I think they are unpublished, but it's very nice because it simulates a neutron star that meets a much smaller black hole. And the result is that at the end, the neutron star the black hole penetrate the neutron star and start to eat it from inside on a rather small time scale. And this somehow triggers some ejection of matter. And actually the paper from John Fuller was actually claiming that that was the large source of our process in the universe. It was before GW 17870. But to my knowledge, this simulation from David Radice is the only one that I've seen, and it's unpublished. But the idea is that the black hole will penetrate and will just eat from the inside the neutron star with a decent amount of ejecta. Because you decompress, it's a hydrodynamics process, and then you just expel. But it's very speculative, I would say. Okay. Okay, so now let's move to short arc gamma reversed. I don't know exactly how much has been said yesterday here about the observational constraint. I will just go quickly through them just to be on the same page. The gamma reversed it's a non-thermal emission that is typically associated with the gamma ray flash. They have been discovered in the end of the 60s by the Vela satellites. They were military satellites, but it was pretty soon clear that they had no human, no anthropological origin. They were coming from the cosmos, from everywhere, from somewhere else compared with the Earth. And since then, I would say that today we can think about the detection of a gamma ray burst not as a spatial event, but something that we can do on a routine base. They are actually observed by X and gamma ray satellites, roughly one every few days. There is the BATSI that was operating during the 90s that has really increased our horizon in terms of gamma ray burst, and nowadays there are these 3 satellites that are actually responsible for the detection of X-ray and gamma ray burst, so the integral, the Swift, and the Fermi. The picture that we have is that it's some phenomena that has some very basic properties that are common, and if you somehow rescale by this property, then you actually end up with a very large variability. For example, these are, you don't see, but it's time, so it's just an example. Here the x-axis is the time, and on the y-axis you have the count of photons, and you can see that they don't really look like there is no clear trend, a clear pattern that it's reproduced. They have a very high intrinsic variability, and on top of that, Bazzi was also able, for example, to understand that they have a cosmological origin because they are distributed actually over the uniform way all over the sky, so they cannot come from the galactic plane. They are at a cosmological origin. This was clear only at the end of the 90s, or during the 90s. If you classify them based on the duration of the burst, so if you introduce this T90 number, which is actually the time that it takes for the burst to emit 90% of the energy, going from 5% to 95%, and then if you plot it as a function of this T90, and this is the number of bursts, already the result of Bazzi was pretty clear that there was two families. So there was the first family where 90% of the emitted was 90% of the energy was emitted within 2 seconds, and look at the peak. The peak is around 0.3 seconds. And there was a second distinct family that had a peak much closer to 100 seconds. And moreover, when people had a look at the spectrum, here you can see all of them. The red line are the short, these guys here. The blue line are the long, these guys here. And as you can see, this is so the amount of photons, the amount of energy emitted per unit centimeters and per unit keV. So it's spectral information. You can see that there is a clear trend. The short seems to have a larger tail. You can see more clearly here, where you can see that the long and the short, they have distinct hardness in the spectrum. So the short tend to have spectra that is on average harder with harder photons, so more energetic photons. So even if you have no idea where they are produced and where do they come from, you still already see that even if they have a lot of common things, there should be at least 2 different categories, if you want, 2 different origins of this. And if you remember one of the numbers that I gave you, I told you that if you have a binary neutron star merger or a black hole neutron star merger and you form a disk, if the disk is an accretion disk and you take an alpha parameter that it's widely accepted, like 0.05, it will take 0.3 seconds, more or less, to accrete that disk. 0.3 seconds. This was one of the initial indications that at least this class of gamma ray burst was connected with the accretion of a stellar-sized neutron star on a black hole. But the revolution in the GRB community came at the end of the 90s, where thanks to the backwater satellites, it was possible not only to detect the burst, but also look and detect what happens after the burst. In particular, on a time scale of a few days after the burst, it was possible to detect the so-called afterglow emission. So in the same position where the burst was localized, it was possible to see a light that was emitted from the X-ray up to the radio, of course varying on a time scale of several, maybe hundreds of days. And what is the point of that? Is that thanks to the afterglow, we have much better resolution in space, and we can actually detect from which galaxy the GRB has been produced. This, of course, has opened a new world, because people could also start to think about, okay, where do they come from? Is there any correlation, for example, between the long and the short and the kind of galaxy that has produced them? And the answer was yes. In the case of the long gamma ray bursts, they were always associated with galaxies with a high star formation rate. And then it was already clear that they should have something to do with massive stars that explode. On the other hand, and in particular this was confirmed at the end of the 90s by the identification of a supernova exactly in the same place where the gamma ray burst and the afterglow were discovered. So there was really the emergence of a supernova from the same place. And this was really the smoking gun that really said long gamma ray bursts are related with supernova. In the case of the short, the thing was a bit more puzzling, or if you want, less clear, because they were actually detected. The first afterglow came later because they are typically fainter, and after that we have collected some of them, and the take-home message is that they happen in all types of galaxies, not only the one with the star formation region, but also the one that do not have any star formation region. This was pointing to the fact that they come from a catastrophic event that involved old objects that are not massive stars because they explode fast. And moreover, as it was also said yesterday, you know, core collapse that form a binary merger typically give a kick. And from this kick, you could expect the binary to leave the galaxy or to leave most of its time outside of the galaxy. And in fact, there was a systematic shift in the position, in the location of the burst, of the short burst with respect to the center of the galaxy. They are actually also fainter and closer, which means that they come at smaller z, smaller cosmological redshift, which means that they come from old population star. And as I said, there was this clear indication that the T90 was comparable with the timescale of the disk. And there was a growing evidence that short gamma ray bursts could have been associated with binary neutron star merger. But I would say that up to 2013, this was still very speculative, if you will. The fact that as the first change the picture was that actually a discovery performed by Neil Tanvir that observing a short gamma ray burst, in particular GRB 130603b, and its afterglow, roughly 10 days after the merger, there was an excess in the infrared. The interpretation that people gave to this event was that it was a short gamma ray burst that produced its afterglow, but behind that, similarly to the case where in the long case you have a supernova that is emerging, in the short you have a kilonova that is emerging. And the kilonova could be the explanation of this excess that deviates from the typical behavior of an afterglow. The doubt that maybe very few people at that time had was really, I think, washed by what we have observed in August 17, where we had clearly the detection of a binary neutron star merger with gravitational waves, followed roughly 2 seconds after by the detection of integer and the Fermi satellites. So I would say that now it's rather robust that binary neutron star merger are the source of sharp gamma ray bursts. Let's have a look at the typical energy. So the solution is not wonderful. I will try just to guide the eye. We can, for example, ask ourselves, what is the energy that is associated with the gamma ray burst? These are things that happen on a cosmological scale. And maybe there are some long gamma ray bursts that have a redshift of 7. So they are really located far away in the universe. And in order to see their light, they must be extremely powerful. Once again, first order, you assume that nature is spherical, the spherical Kaplan model. And then you say, if I get from the photon a certain amount, if I get on the Earth a certain amount of photons, I can assume that the source that has generated this photon, it's emitting the same amount of energy over the whole sky. This is the so-called isotropic energy. It's 4 pi, the luminosity distance squared, times the so-called fluence. In terms of luminosity, you have to put the flux. If you now compute this quantity for the gamma ray burst, and the short are just the square, the blue square here, you will end up with energy of the order of 10 to the 51, 10 to the 52. For the long, you will end up with 10 to the 54. Just to give you a scale, if you take the sun and you annihilate it instantaneously into energy, this will give you 10 to the 54 Earth. So the energy associated with some long GRB, it's more than the energy that you will get if you annihilate instantaneously the whole sun. It was clear that it was too much in some sense. So people understood immediately, well, not immediately, but it was clear that in order to reconcile what we have observed with the possible phenomena that happens in nature, we don't have to assume once again spherical symmetry. In particular, what happens if the jet is emitted, if the energy is emitted along a jet? Then the true energy, we have to correct for the so-called beaming factor. The fact that this energy is only emitted in a portion of the solid angle. This is delta omega over 4 pi. And if you assume, for example, that the jet has an opening angle of 10 degrees, you have to divide the isotropic energy that comes from here by a factor of 65. Okay? So really, if you take into account that maybe that matter is not ejected in 4 pi, but only in a jet, so in a cone, if you want, double cone, actually you can correct by a factor of at least 100. Actually, recent observations indicate that the jet could have an opening angle even smaller than 10 degrees. There are few of them, it's very challenging, it's a very debate how to measure the opening angle, but the few that we can measure in the short case are of the order of 6 degrees. Okay, so we have to heavily correct because it's quadratic in the opening. So far, I just made this very brief introduction from somebody that knows very few things about observation, about the result of, say, of what we observe in gamma ray burst in 40 years of activity. But so far I didn't tell you where do they come from, what is the physical picture that we have in mind. Now in the rest I will try actually to explain what is the present knowledge of how a gamma ray burst is produced. The model that is more popular, it's a so-called fireball model. This is actually a model that tells you how the gamma ray burst is produced. It doesn't say anything about the central energy. This is a separate problem that we will tackle, let's say, in a quarter of an hour. But for the time being, I'm just interested to know how the gamma rays are produced. Okay? So we have to break our problem into small pieces. And in order to understand how the gamma rays are produced, people came out with this fireball model. Of course, we will not deal with, this is a long gamma ray burst, we will deal with the short, but as you can see, it's common to both of them because they have similar features. So something happens, let's say that way. We call this the central engine. The first things that you need from an engine is to extract energy from it. So the first phase is called energy injection. We assume that there are some stellar-sized object that undergoes an event that is very catastrophic. Very catastrophic means that there are a lot of energy that is released in a small amount of time. Okay? We deposit an amount of energy that is a few times the energy that later will power the gamma ray burst, because we have always to be conservative, you know. If you deposit a certain amount of energy, it's hard that all that energy will be measured as a gamma ray burst. There will be maybe several ways in which this energy can actually be, let's say, can leak actually from the system. So we need at least a few times the energy through that I introduced before, and this must be actually released on an amount of time that is comparable to this T90. And this happens on a very small time scale. So this is of course not in scale or sort of logarithmic scale. So this injection phase will happen here. This huge amount of energy will be actually emitted in a rather small area. This is 10 kilometers, this is 100 kilometers. Whenever you put such a small amount of energy in such high amount of energy in such a small amount of place, of course you will have a huge density of energy. So you will form actually a fireball. What is a fireball? It's a plasma made of heat, radiation, and electromagnetic field, and particles. I think we have got particles, of course. There will be baryons, because the universe is made out of baryons. And the energy is so high that you will produce a lot of electron positrons, and the electron positron will keep your photon trapped. Okay? So you will have something that it's really a fireball in the sense that all the components, the magnetic field, the photons, and the baryons are trapped inside because of this huge amount of energy. In particular, we introduce this eta parameter. Eta parameter is the ratio between the energy that we inject and the mass that the fireball has. As we will see later, we will require that this must be much larger than 1. In principle, this is not necessary. We could have also fireball where this is smaller than 1, but then we will not produce a gamma ray burst. Okay, I will tell you later. Now, just keep in mind that this ratio here is defined in this way, and it has to be much larger than 1. Whenever you have this fireball, you will have a lot of internal energy, a lot of pressure. This pressure will just make PDV work, and will just make all your matter expand up to relativistic velocity. In particular, there are a lot of analytic solutions to this problem, and also nowadays also numerical solution. And the result is that whenever you go to high speed, you can always associate a gamma factor, the gamma that comes from the special relativity if you want. And the solution of the hydrodynamics equation tells you that the gamma factor that the jet has once it has reached its asymptotic behavior is exactly of the same order as the eta that I introduced here. Okay? So in order to be ultra-relativistic, that's why I need eta to be much larger than 1. Otherwise, the jet will not be ultra-relativistic. In the following, I will assume that matter dominates. In the sense that I told you that there will be baryons, there will be photons, there will be electron positrons, and there will be magnetic fields. In the standard fireball model, people assume that the magnetic field is subdominant. So if you calculate the density of the magnetic fields divided by the rest mass density, you will see that this number is much smaller than 1, which means that the density, the energy, the kinetic, and the rest mass density of the jet overcome the variable density. This is just an assumption that we have to make. I will tell you later what happens if we change this assumption. So this is where we deposit the energy. The energy gets accelerated, and of course, whenever you accelerate, the density drops. And there will be a point where, exactly like in the Kilonovae scenario, there is a point where photons are no more trapped. You become optically thin, and then the photons can actually be emitted. You can think about that, okay, that's the explanation of the gamma ray burst. I just put a lot of energy, this energy expands. At a certain point, the energy, it's like a kilonova. The energy expands and will be emitted. However, we have two problems. The kind of emission that we would have in that case could be thermal, because this is energy that comes from a photosphere. And the second point is that you have to compute how much energy, and it's way too small compared with the energy of the gamma ray burst. So this is called the pre-burst emission that you can see here, but it's actually not the burst itself. It's an emission that could come before, and but it's not the burst itself. So where does this energy come from, the burst? When you think about this kind of jet, you don't have to think about something that is homogeneous, that it's just, you know, a flow like a river, that it's just flowing from the center to the end. You have more to think about something that emits some matter and then stop. Emit matter and stop. So something that it's like the engine is working a bit on, off. And every time it works, it just ejects matter with a certain velocity. The velocity does not need to be the same all the time. You could emit a blob with a smaller velocity, and then you emit a blob with a faster velocity. The blob with the fast velocity that was emitted later will catch up at the first one, and will just crash on it. This hydrodynamical interaction will produce the so-called internal shocks. In these internal shocks, the jet converts its kinetic energy into internal energy. This conversion is what actually emits the photons that we see as gamma ray. Okay? So the gamma ray burst comes from the development of the shocks inside the jet when matter moving at different speed just collide with each other. Okay, this is what we think at the moment is the origin of the gamma rays. So there is this dissipation of energy in internal shocks. Then what happens is that in these shocks, the magnetic fields get locally amplified. The electrons that moves in these amplified magnetic fields emit synchrotron radiation, and this synchrotron radiation from these high energy photons produces the gamma ray emission. Okay, so this is the picture. Internal energy, so kinetic energy becomes internal energy that gets into magnetic fields, and the electrons moving in these magnetic fields emit synchrotron radiation. This is actually what is happening here. I told you that it could be that the jet has more energy than the one that we see in the gamma ray. What does it mean? It means that after the gamma ray emission, what is the so-called prompt emission, the jet does not stop. It has still a lot of kinetic energy and keep on expanding inside the interstellar medium. The expansion of the jet inside the interstellar medium causes the jet to slow down. So the jet dissipates its kinetic energy on a much longer time scale and on much wider time scale, length scale inside the interstellar medium. Once again, the interaction produces some shock. Now they are called external shock because they are no more inside the jet, but they are between the jet and the interstellar medium. This amplifies again locally the magnetic fields. The electrons again emit by synchrotron radiation. However, the energy of the shock is much smaller now, so you don't produce any more gamma rays, but you produce X-ray, the visible, ultraviolet, visible, up to X-ray. This is what we think is the origin of the afterglow. So interaction between the jet and the interstellar medium that amplifies again magnetic fields, and then you have synchrotron radiation that produces at decreasing energy your photons. This is just 5-step the fireball model that should explain the prompt emission and the afterglow. Let's try to be a bit more quantitative in what we said. Try just to, it's still some order of magnitude estimate, but I think it's more. If we just look at the observation, gamma ray bursts are objects that have a very intrinsic variability. So if you just look at the spectrum, you will see that there are some features that have a typical length scale, time scale of the order of 1 millisecond. So this means that it's an object that has this kind of variability. Moreover, the energy that we observe is of the order of 1 MeV, because they are gamma, well, maybe a few hundreds of keV, but they are very energetic. If you now take these two numbers together and you just make some very simple argument, you end up with a problem that is called the so-called compactness problem. What is this problem? If you see a variability of the order of 1 millisecond, you must assume that your central engine, or the place where the photons are, well, no, not the central engine, the place where the photons are produced, must be causally connected on a time scale of this order here, which means that the size of this object must be of the order of delta t times c. This is the only way in which a system can have such a kind of variability. And this ends up with 10 to the 7 centimeters, so 100 kilometers. But if you now put 1 MeV photons in such a small thing, you will produce a lot of electrons and positrons that will just thermalize anything. So the kind of emission that we expect from such a fireball is thermal. It's what I said at the beginning. Why do we have something? This is the spectrum of a GRE. This is highly non-thermal. It should have it has a much lower, much larger tail compared with what we expect from a thermal emission. How can we reconcile these two concepts? This is the so-called compactness problem. And the way out here is assuming that matter is moving relativistically. Why? First of all, if matter is moving relativistically, in the rest frame of the particle that emits the matter, you can produce photons at a lower energy. The relative motion, due to the fact that you are moving at relativistic speed with respect to the Earth, will just make a boost of the energy given by the gamma factor. So the energy that we observe of the order of 1 MeV has actually been boosted by the energy that was produced in the rest frame. Okay? So in the rest frame, we don't have 1 MeV photons. We have photons that are maybe 1 keV or even lower. And if the energy of the photon is 1 keV in the rest frame, it's not so easy to produce an electron-positron pair, because you need, at least 1 MeV to produce an electron-positron pair. So first thing. The second thing is that if a system is boosted, also the time gets delayed. The time you have the time dilatation due to the special relativistic effect. So the variability that we observe must be corrected also by a second power of the gamma. And so the size of the system is actually potentially much larger than that because of this gamma factor here. So if you want your matter to become transparent in a region where the photons are not produced with 1 MeV energy but with a smaller energy such that they don't get trapped in electron-positron plasma, you will end up that if you get a gamma of 100, there is no problem. If you have a Lorentz factor of 100, you can easily produce your photons that will be then boosted to larger energy, and they will be produced by a larger source, such that you don't have any more the compactness. Okay? However, there is a price that we have to pay. If you remember, I told you that the asymptotic gamma that the jet reaches must be of the order of eta. Eta was the ratio between the energy and the baryonic mass of the jet. If you want to accelerate the jet to 100, eta must be 100. It means that we have to deposit our energy in a relatively baryon-free environment. In particular, if you just plug in the numbers in this formula, the mass of the jet must be something of the order of 6 times 10 to the minus 6 the mass of the sun. So you are colliding two neutron stars, for example. This will eject maybe a fraction of a solar mass in the ejecta, but you have to be sure that there is a place in this central engine where the amount of baryon is smaller than 10 to the minus 6. Otherwise, if you deposit the energy, you will never get a relativistic jet. This is highly non-trivial, okay? Because it's very hard to keep the system clean of baryons. So people start to investigate, okay, Okay, you told us the observation, you told us the Faraday models, but you didn't tell us what is causing this energy deposition. We still have the big question for the modelist. What is really causing the jet? What is really causing this energy deposition in a baryon-free environment? And there are actually, so there is no clear answer to this question, but there are at least 2 or 3 different scenarios that can explain this. I will just show 3 of them that are actually the favorite. The first one is sketched here. So you have to assume that in the center, the massive neutron star has collapsed, or we have a black hole since the beginning because it's a black hole neutron star merger. It's surrounded by a disk,